Okay, dear participants, we'll begin the seminar in about 1 or 2 minutes. In the meantime, we are allowing a few more minutes for everyone to join. A quick reminder, please make sure your Zoom display name matches your full name as used during the registration, first name plus last name. By joining this session, you are considered to have accepted a data privacy consent as part of your registration process. During the session, you may ask your questions either by unmuting yourself and speaking directly to the presenter, or by using the Q&A or chat sections. And thank you for your participation. We will get started shortly. Okay, hello everyone. Today marks the final session, the bonus session of 5 Beats of Intelligence AI Meets Diverse Domains seminar series, a collaborative initiative under the EuroCC-4C project, exploring the intersections of AI and various domains. In this bonus seminar titled AI Meets Precision Agriculture, we are pleased to welcome Ivan Jovovic as our guest speaker. Ivan is a PhD student, teaching assistant, and a research associate at the University of Donja, Gorica, Montenegro, with a strong background in applying AI, edge computing, and HPC technologies to real-world challenges in agriculture. Today's session will delve into how artificial intelligence, computer vision, and high-performance computing are being leveraged to optimize agricultural processes, particularly in developing AI IoT solutions for precision farming. The presentation will highlight case studies involving computer vision and the use of synthetic data sets to enhance prediction models and support data-driven decision-making in agricultural sector, if I'm correct. We thank you for joining us on this final beat of series and look forward to an inspiring discussion. Ivan, if you're ready, thank you again for joining us today, and the floor is yours.
Yes, thank you, Susan. Let me just share my presentation. So can you see my presentation?
Again, we have the strip on the top. Yes, that's...
So you can see it now?
Yes, but we cannot see the titles on the top, if there's any.
So you can see them now, I assume.
Yes, perfect. Thank you.
Hello, everyone. My name is Ivan Jovovic, and I am PhD student at University of Donja Gorica, and also part of NCC Montenegro. It is a great pleasure to be here at this EuroCC workshop, especially in the context of discussing sustainable and secure AI. So today I will talk about artificial intelligence and precision agriculture. But before we dive deeper into this topic, I would like to briefly introduce our core technical team at AI and HPC department at UDG. So this is the team behind many of our AI solutions and research efforts, combining expertise in computer vision, edge computing, neuroscience, medicine, energy, education, as you can see. And all of this is powered by high-performance computing. So as you can see, the team is led by Dr. Tomo Popovic, and it includes an amazing mix of skills and applied focus areas, all of which play a role in the work that I'll present today. You already had a chance to meet my colleague, Dejan Babic, who presented about AI in biomarkers. So I'm going to go to the next slide. So I'm going to talk about Aim High project, which we did. In this project, we are building an edge AI computer vision kit that is designed specifically for smart poultry farms. So the main idea of this project was pretty simple. We trained powerful deep learning models using HPC and then deploy those models to small energy efficient devices right there at the farm. So those devices can work in real time, keeping an eye on things like chicken's health, movement, behavior, etc. So the goal was to create a scalable system that will help farmers reduce that manual work, try to boost productivity, and to improve the overall well-being of the animals. So as you can see at the footer of this slide, we had a help from the farm partners and industry partners such as Dunavnet, Digital Smart, Franca, and Radinovic. And I think this is a project that is a great example of how combination of AI or computer vision edge devices and HPC can come together to solve real-world problems in agriculture. So before I start with this project and specific solution, I just want to take a moment to show how AI is already reshaping agriculture in, let's say, practical ways. So we are witnesses that across farms of all sizes, we can see AI being used in all kinds of innovative ways, from predicting weather patterns with remarkable accuracy, monitoring soil conditions, crop health in real time, and even supporting precise decision-making in daily farm operations. So we also can see drones that are becoming the eyes of any modern farm that are flying overhead to collect detailed aerial imagery. Then AI processes it to detect problems like disease, stress, uneven growth, etc. Also, we can see AI-powered robots that are stepping into the field, quite literally. They are helping automating tasks such as planting, harvesting, sorting, producing, especially in the areas where labor shortages are in serious challenge. So also we now have AI surveillance systems, smart cameras, sensors that keep constant watch over crops or livestock. And those are supposed to flag anything out of the ordinary. So that might be a change in animal behavior, a drop in feed consumption, a potential security issue, and similar problems. So I'm going to go to the next slide. So what challenges are we willing to solve here? So the most obvious challenge, and the first one, is the global demand for food is growing rapidly, especially when it comes to animal protein. So as populations rise and diets change, pressure on meat production system is increasing, and poultry is right there at the center of the growth. So the question is how we scale and optimize animal farming process in the way that meets demands, but also remains efficient, human, and sustainable. So traditional farming methods alone can keep up. They are labor intensive, inconsistent, and often reactive rather than proactive, if I can say that. So that's where we believe AI has a really big role to play. And the third, as I mentioned before, and most important question is, can we use AI especially with those latest advancements in edge computing and computer vision to help farmers make better and faster decisions. So the main focus in our research was poultry farms, as I said, and more precisely on the everyday challenges that farmers face when raising chickens at scale. So one of the biggest concerns in the early detection of disease outbreaks. Illness can spread quickly and impact environments, and even a short delay in identifying those symptoms can lead to significant losses. Another issue is the presence of dead chickens that go unnoticed. Not only this is a health risk for the rest of the flock, but it also signals that something might be going wrong with the environment, with the feeding system, or the overall health of the animals. Beyond these critical alerts that I mentioned, we also looked on how to track and monitor the basic life necessities, such as whether the chicken have access to enough food and water, is the lighting functioning properly, or if the air quality and temperature are within the healthy ranges. So our main focus is like twofold. First, to support farmers in reacting faster and more precisely to these issues before they become seriously problematic. And the second is to ensure that the entire process respects and promotes animal welfare while also making farm management more efficient and less stressful for the people involved. So our main research goals, first and foremost, we wanted to develop smart camera-based sensors on poultry farms. So these sensors use deep learning to process images directly on the site using edge devices. That means that they don't rely on internet connectivity or sending data to the cloud, and everything happens locally and in the real time. So to make this possible, we heavily relied on high-performance computing. That HPC allowed us to train our models faster and with more complexity, which is really, really important when you are working with video feeds, object detection, and behavior tracking. So once trained, these models are then deployed to small edge devices. We were using NVIDIA Jetson Nano device, and they are directly connected to the camera sensor placed through the poultry farm. So these systems are supposed to be designed to run 24/7 with minimal maintenance. And finally, we wanted to make sure that all of this ties together somehow. So we also worked on integrating our AI models into user-friendly web applications, where farmers can monitor alerts, review detected events, and somehow gain insight into the overall status of the farm. So in essence, the goal was to bring together deep learning, IoT, edge computing, and HPC, and to make it all work in some practical applied agricultural settings. So when we break our research down into concrete tasks, it all starts with object detection. So we train models that can identify and count chickens in each frame. So this gives us real-time insights into flock density and movement. We also focused on detecting dead chickens, which is one of the most critical, let's say, early indicators that something is going wrong. Along detection, we also did object segmentation, which helps us outline the exact shape of each chicken. From there, we estimate individual body weight of each chicken, which is useful proxy for growth rate, health, and feed efficiency. And to make our development process faster and more efficient, we used AutoML techniques, especially for hyperparameter optimization. So this allowed us to fine-tune model performance without manually testing endless combinations. And the most recent part of our study, our project, was exploring generative AI to help address one of the big bottlenecks in AI development, the lack of quality annotated data. So we were trying to generate synthetic poultry farm images so we can train our models more, let's say, robustly, even when the real world data is limited. So you can see how we structure the entire implementation process from concept to the final deployment. So phase one was all about design. We began by gathering requirements directly from the farmers and farms, identifying real challenges and planning our experiments accordingly. So this helped us understand what kind of data we needed, what sensors should detect, what features were the most important for the farmers, etc. In phase two, we moved into the model development phase using HPC to train our models efficiently. So these models had to be accurate, lightweight enough to run on edge devices, and robust enough to real-world variability, such as different lighting or different positions of the chicken. Once we had working models, phase three was focused on integration. We deployed AI-powered camera nodes on the real poultry farms where they run autonomously, and we tried to provide real-time decision support. Phase four, we turned to validation. So testing the system in different conditions, we tried to ensure some accuracy and low error rates. This was done in collaboration, as I said, with our industry partners, Radinovic and Franza, to make sure that this technology, this tech, is truly working on site. And the final phase five is supposed to deal with a broader picture, such as project management, sharing results with the wider research and farming communities, and looking at opportunities to somehow scale and apply these solutions beyond just one or two farms. So this is a simplified architecture of our project or our design, showing the full pipeline from the farm to the model and back. So everything starts at the poultry farm, as you can see, where camera sensors continuously capture images of the chickens. So these sensors are connected to IoT edge devices, in our case, as I mentioned, Jetson on board, that are capable of running AI models right there on the site. So the raw image data collected from the farms is sent to our data pipeline. First, we annotate the images using SWAT. I will mention SWAT later. And then we pre-process and augment the data using RoboFlow to expand our data set and to make the models more alike to our real-world conditions. So from there, the prepared data set is fed into our training environment, where we use frameworks such as Detectron 2 and models such as faster RCNN. So this part was also powered by HPC infrastructure. At that time, we used Iota cluster from Rijeka to speed our model training and experimentation. And once we trained and validated the best performing models, they are deployed back to edge devices and they can operate in real time. So this was just a simplified architecture. This is the second diagram that shows a more detailed view of the architecture, highlighting how we can handle both offline training and real-time inference in practice. So at the top of this diagram, you can see where it all begins with data captured from sensors and cameras, as I mentioned before. And I will focus on the left side. We enter the offline loop, where the data is used to train AI models. This training happens on our HPC computing infrastructure, HPC infrastructure. We use powerful resources that can optimize those models. So the result of this process is supposed to be a well-trained model, what we can call the offline model in our case, and that is ready for deployment. So that model is then pushed to the online loop that is shown on the right, and this is where the real action happens. So the trained model runs on Edge kit that is installed on the farm and performs real-time image analysis. It detects, classifies, and monitors what's happening with the chickens directly on the device. So the outputs are then post-processed and fed into several tools, including image analytics, decision support dashboards, alerts, and historical databases and reports to help farmers monitor those trends over time. So what we can see here is a closed loop system. So the offline loop is there to improve the model over time, while the online loop delivers immediate insights on the ground, on the farm. So to build reliable models, we needed a strong data set, and we started with extending the original DunaNet, our partner data set, with the new data that is collected directly from our partners' farms. So for the object detection part of our work, which includes things like counting chickens and detecting dead ones, we annotated over 4,000 images, and after applying various data augmentation techniques such as rotation, scaling, brightness adjustment, and more, we increased this data set to 10,000 images. And for the object segmentation or instance segmentation, where we are supposed to identify the precise outlines of each chicken to estimate things like body size and weight, we labeled over 1,000 images and expanded that set to 2,500 after augmentation. So you can see on the right side of this slide how that data is looking like. So definitely building and cleaning these data sets took a long time. So for the purpose of data labeling, we used CVAT, as I previously mentioned before. CVAT is a computer vision annotation tool that is an open source annotation tool that we use to label thousands of images for object detection. And as you can see here, each chicken in the image is manually marked with a bounding box and tagged with the appropriate class in the label. In this class, chicken. So this step might seem simple, but it's actually very, very time consuming and critical. So the quality of the model, as you already know, is only as good as the quality of the data you feed it. So consistent and accurate labeling is crucial. So we also took care of varied samples with different lightnings, with positions, with partial occlusions, so that the model could learn to generalize better. So this is the next level of data labeling, where we are doing object segmentation or instance segmentation, to be more precise. So instead of just drawing boxes around chickens like in object detection, we try to create precise outlines that follow the exact shape of each chicken. So you can see clearly here in SWAT that each chicken is segmented with a custom polygon mask. So this approach gives us more detailed information. For example, by calculating the area of each mask, we can estimate the relative size or weight of each chicken over time. That kind of data is especially valuable for tracking growth, monitoring health, or spotting those underdeveloped chickens. So it also improves the performance of downstream models, especially when chickens overlap, move unpredictably, or appear at some weird or odd angles. So once we had our data set ready, we started with exploring different deep learning models, both for object detection and instance segmentation. So all of this was done on high-performance computing system, which allowed us to experiment much faster. And over the course of this project, we ran more than 3,000 training experiments using single or multiple GPUs, tweaking architectures, augmentations, loss functions, and more. So one of the key tools that we used to make this manageable was AutoML and hyperparameter optimization. So instead of manually tuning learning rates, batch sizes, we used automation to fine-tune model parameters, improve accuracy, and reduce training time. So on the right side, you can see the examples of what the trained models produce, bounding boxes with a class confidence of detection. And as you can see also in the right bottom, we can see a pixel accurate masks for segmentation. So let me just quickly talk about Swarm and HPC. To handle the amount of data and the number of all those experiments that we run, we relied on HPC environment that was provided by Yotta, which was using, as you can see, NVIDIA Tesla M60 GPUs. So the key tool that we used for managing all those jobs was Swarm, which stands for Simple Linux Utility for Resource Management, if I'm correct. So that's an open source workload that helps us to distribute jobs across available nodes in the cluster. So the process is pretty straightforward. We log into the node with SSH, which is something like command center, but we don't run any heavy computations there. Instead, we use Swarm commands such as sbatch or salloc to schedule jobs to run on the actual compute nodes, those that are equipped with GPUs and that are optimized for parallel processing. So Swarm takes care of allocating resources, monitoring execution, and managing queues, so that we can run thousands of model training jobs without crashing the system or stepping on each other's experiments. So it's obvious that without this kind of infrastructure, it could be almost impossible to train and to test so many models efficiently, especially when we are dealing with deep learning models such as faster RCNN or mask RCNN, which are very computationally demanding. So on this slide, you can see a real example of one of our Slurm jobs script looks like when we submit it to the cluster. At the top, you can see the Slurm directives. These define the job's configurations. So as you can see, we are requesting one node. We set time limit of 360 hours, and we specify that these jobs should go to GPU partition, and we need 8 GPUs for the process of training. So below that, we can see that we need to load software modules such as Python, CUDA, all those models that can ensure that environment is compatible with libraries such as PyTorch, Torch Vision, and Detectron 2, which we used for this experiment. So to optimize both object detection and instance segmentation, we ran some extensive loops that tested different hyperparameter combinations. On the left side of this slide, you can see object detection tuning loop. So it goes through different combinations of GPU counts, so 1, 2, 4, and 8, and model architectures, batch sizes, and it's constantly checking which setup gives us the best ratio of accuracy to prediction time. On the right is the loop we used for fine-tuning one selected architecture. Here you can see we iterated over different values for batch size, for gamma parameter, and for learning rate decay parameter to try to further improve precision. So once we found the combination with the best average precision, then we selected it as a final model. So this is for object detection, and we applied the same logic for the instance segmentation, just using a different set of models like mask RCNN. So exactly this approach led us to perform over 3,000 training runs that are systematically, let's say, narrowing down to the most efficient and most accurate model. So on this slide, you can see the results of that extensive work for object detection. We used faster RCNN models in Detectron 2. So on the left side of this slide, table 1 is showing how different architectures like R50 or R101 with or without FPN performed under different GPU configurations. So it tracked several key metrics such as training time, validation loss, average precision, and maybe the most importantly, prediction time per image, since it's supposed to work in real time. So for instance, the R101 FPN architecture was trained with 4 GPUs and the batch size of 4, gave us a strong average precision of 83.41, as you can see, with a very, very short training time of just 17 minutes. But as I mentioned before, accuracy alone wasn't enough. So we also considered prediction speed and resource efficiency, which is crucial for real-time deployment. And on the right side, table 2 shows our hyperparameter tuning for the one selected architecture, which was best for us, R101 FPN. And there we tested the different combinations of gamma values, batch sizes, GPU counts, and we try to measure how each setting is impacting both performance and speed. So one interesting takeaway that can be seen in this slide is that with increasing the number of GPUs, we don't always have guaranteed higher accuracy, but it does significantly reduce training time, which is essential in these projects where we are testing thousands of combinations like we did. So this is the second part of our experiment where we decided to try making some models with the famous YOLO algorithm. So before selecting the most suitable model for our system, we analyzed the performance of the latest object detection architectures. So as you can see, this benchmark that was published by Ultralytics can show a trade-off between accuracy and latency across different YOLO versions and some other models. So this analysis guided our decision to experiment with YOLO v9e and YOLO v9 seg. So those are the two of the most balanced models in terms of real-time accuracy and deployment readiness. So, as I said before, based on the benchmark insights, we trained two specialized models on our dataset of all three images. So YOLO V9E for object detection and YOLO V9 SEG for instance segmentations. So the graphs on the left show training and validation curves for the detection model. So we can observe a steady convergence, to say it like that, of the loss function and excellent classification, and also localization metrics with the mean average precision exceeding 93%. So on the right, we can see the segmentation model performance, precision, and recall are both constantly high across both bounding boxes and masked predictions. And it results in segmentation mean average precision above 90%, which is definitely remarkable for real-world scenes. So these results confirmed that YOLO V9 is offering a powerful and very efficient solution for this type of tasks. So, as I said, maybe at the start of this presentation, we were recently experimenting with generative AI. And this slide is showing how that generative AI is fitting into the broader architecture system architecture. So we used generative AI to create a synthetic data set to complement the real-world data that we collected on the farms. So after pre-processing, annotation, and optional augmentation, the data is fed to the training pipeline where models like YOLO V9 are fine-tuned. So as mentioned previously, these trained models are deployed to edge devices for real-time inference. So one edge device is handling a data collection, while the other is performing prediction on site using camera feeds. Those results are then transmitted via API to the cloud platform. So this architecture is now enabling a seamless loop from synthetic data generation to real-world deployment, and it's supposed to demonstrate how generative AI can, let's say, accelerate and maybe enrich that precision farming that is powered by AI. So if you want to hear more or read more details about this, you can find our recent paper that is published in Applied Sciences, where we evaluated the impact of synthetic data on YOLO V9 performance. So building on our initial experiments with Gen AI, this diagram outlines that the full cycle of how synthetic data is integrated into the pipeline, and more importantly, how the system continuously improves over the time. So everything starts with real-world data as always, using cameras and sensors on the farm. So that raw input goes through several pre-processing stages, and from there we enter the generative AI phase. So based on our needs, we selected a generative model like DALE 3 or Flux 1 and fine-tune it through some kind of iterative training. So that allowed us to generate synthetic images that complement the original data set and help fill gaps or simulate some edge cases. So the synthetic image generation process is prompt-driven, and it's followed by evaluation by human experts or maybe AI-assisted validators. So this step is supposed to ensure that only the most useful and realistic synthetic images enter the model training pipeline. And then this cycle is loops, model outputs are tested, insights are fed back into the annotation and training stages, and the system is refined further. So on this slide, you can see a concrete example of how our Gen AI setup translates that text prompt into synthetic images. So on the left side is the exact configuration that we used, starting with a detailed prompt describing the scene, including light, as you can see, texture, object position, behavior. So in this case, the prompt focuses on realistic close-up of the chickens in a very, very filled environment, specifying aspects like fluffiness, color variation, and behavior to mimic real farm conditions. So we also define the resolution, number of outputs, image format, inference steps, and other parameters like guidance scale and prompt strength, which helped us fine-tune how closely this output follows the textual description. So on the right side, or in the middle, I don't know, you can see the resulting synthetic images that are generated entirely from the single prompt. So these images, as you can see, not only match our real-world distribution, but also offer additional variability that can help us improve generalization in our models. So this process definitely significantly accelerated dataset creation while keeping quality control in our hands. So this slide presents the algorithmic blueprint behind this effort. First, we begin by collecting and selecting a portion of the real data set, which serves as our foundation. From there, we load and fine-tune our chosen generative model. In this case, we used Flux 1.1, which was in development stage, and we use a different set of parameters. So notice the use of the custom trigger word, which we defined as chickrad, which means Chicken Radinovic, the farm where we collected the data and worked with. We introduced that trigger word during training to condition the model on poultry-specific visual patterns. So with the LoRa rank of 16 and 1,000 training steps, we ensured that model could adapt quickly while trying to retain generalization. So once the model was fine-tuned, we moved into the generation phase, carefully selecting hyperparameters, guidance scale, prompt strength to steer that output toward high-quality, realistic chicken imaging. So the prompt that you can see here at the bottom of the slide is this exact one that we used to generate previously shown images. So in short, we were trying to taught the machine, the computer, to try to imagine chickens based on real examples, refined prompts, and let's say structured creativity. So after training those generative models and creating synthetic chicken imagery, the next logical step was to ask, does that data really help? So this table summarizes the result of carefully designed series of experiments that are trying to evaluate the impact of synthetic data on the accuracy of Jovovic model. So we started testing on 50 real images in consistent settings, 100 epochs, and a batch size of 16. So as you can see in experiment one, that was our baseline, we had no data at all, and unsurprisingly, this mean average precision is very, very low, around 20%. So from there, we tried to gradually explore different combinations using only real data, which is experiment 3, gave us a strong performance, about 0.82 mean average precision. So interestingly, even when using only synthetic data, which can be seen in experiment 5, where we use 400 images of synthetic data, we approach similar model performance, about 0.8 mean average precision, that this is highlighting the high realism of generated data. So the most impressive results, however, came from the hybrid configurations. For example, experiment 8, where we combine 300 real images and 100 synthetic, achieves the highest mean average precision of 83. So what we also explored in experiment 10 through 15 is the idea of augmenting existing datasets, adding 800 synthetic images to the base of real data. So across this, performance also remains strong and consistent. And that suggests that synthetic augmentation is a reliable strategy for boosting accuracy, especially when scaling up data is expensive or impractical. So, as I mentioned before at the beginning, we were experimenting not only with generative AI, but also with various tools for automated image processing. This slide shows the results of automatic annotation using the grounding dyno model. This model performs object detection and labeling. So in this case, it identifies chicken in complex scenes. So as you can see, the model managed to detect 21 out of 29 chickens using a relatively low confidence threshold of 25%. So this is impressive given the dense and partially occluded arrangements of chickens. So this method significantly accelerated our labeling process, especially for large data sets, and it served as an additional layer of validation for model accuracy. So I mentioned the platform before. This was done by DunamNet company. So once the models were trained, evaluated, and fine-tuned, both on real and synthetic data, the next step was full platform integration. So what you can see here is AgroNet platform, where the results of our models segmentation were seamlessly integrated to provide real-time insights directly within the farm. So each chicken is detected, segmented, and tracked with almost 100% confidence, and the visual data is paired with timestamps, identification codes, and it's supposed to help farmers monitor flock density, movement, and behavior. So also on the right side, you can see historical snapshots that allow for temporal analysis, making it easier to evaluate trends or to detect anomalies over time. So one of the practical applications of our system is the automatic measurements of occupancy density. So it's supposed to estimate how crowded specific areas of the poultry house are at any given time. So this is done by processing video frames from multiple camera positions using instance segmentation models. So in our case, models like Jovovic, and those identifying count individual chickens in the frame. So then using a very known field of view and pixel area to real area ratio, we are trying to compute the percentage of the visible floor space that is covered by chicken. So for example, a frame that is showing 60% occupancy means that approximately 60% of the ground area in the camera's view is occupied by chickens. So the metric is important. This metric is important for monitoring animal welfare, detecting some signs of overcrowding or underutilization, and adjusting space usage dynamically. So as you can see here, farmer can see real-time occupancy percentages from 34, 61, 20, and so on across different zones. So these values are automatically updated, and they provide some kind of heat map style overview that allows for better ventilation control, feeding system placements, and overall environmental management. So as we come to an almost end, here are the key outcomes of our work so far. So firstly, we annotated a large data set that is including thousands of images, both real and synthetic, significantly expanding the original DunarNet dataset. Then we carefully selected the optimal model architecture and tuning parameters to maximize performance and efficiency on edge devices. After that, the models were successfully deployed to an IoT AI edge platform, and then we achieved seamless integration with the commercial agronet system, reaching over 90% accuracy in detection tasks. So our models were also validated in the field with real images and feedback from end users. And one of the most promising, let's say, aspects was the use of generative AI, which showed real potential in reducing that dependence on real-world data collection. So, and finally, as we are actively expanding our research, we are particularly focusing on the estimation of the poultry weight with AI and vision-based cues. This is the next part of our project, and I think this is it's expected for this to be a major step forward in automated farm management. So that will be all from my side. Thank you for your attention.
Thank you, Ivan, for your presentation and your contribution. Do our guest participants have any questions or comments? If not, let me start with my question, very general one. You mentioned that you use the power of high-performance computing in your work, and are you running these computations in your work on your local workstations, or do you also use some supercomputing center like EuroHPC supercomputers or so?
Yes, Susan, as I mentioned before, for the initial part of this experiment, we use Iota cluster in Rijeka. Now at UDG, we have some kind of HPC infrastructure, and we use that for our initial experiments. Also, we have access to some of supercomputers in the Europe, such as Lumi, and we will try to use all those resources for further experiments.
Through some access calls, I guess.
Yes, of course.
Any questions or comments? No. If you have anything, then you can reach either us or Ivan directly via his email, or some you can use maybe LinkedIn or some other communication channels to ask your questions. And then let us thank Ivan again for today's contribution. Ivan, do you have anything to add or say as last words?
Nothing from my side, Suzanne. It was my honor to be part of this seminar.
Okay, thank you, Ivan. So, as we conclude the 5 Beats of Intelligence AI Meets Diverse Domain Seminar Series, we would like to sincerely, as NCC Turkey, sincerely thank all of our colleagues from the EuroCC-4C countries for their valuable contributions and commitment through this journey. Your efforts, my colleagues' efforts from Serbia, North Macedonia, Montenegro, and Bosnia and Herzegovina have been essential in shaping this series into a meaningful and collaborative initiative. And the seminar series is more than just a set of presentations. It's a reflection of healthy organic partnerships we continue to build across our national competence centers. Following the strong interest in last year's machine learning training, this series stands as further evidence of growing and effective collaboration among us. Thank you. We see this initiative as a first step towards future joint efforts, and we look forward to developing new ideas together. All materials and video recordings from this series are available on the respective event pages and on our YouTube channel, so participants can revisit or catch up on any session. We welcome your suggestions, our participants' suggestions for future online or on-site events, and feel free to contact us through any of our communication channels via NCC mailing addresses, LinkedIn, Instagram, every communication channels that you can use. Once again, our heartfelt thanks go to all organizing countries, Serbia, Montenegro, North Macedonia, Bosnia, and to everyone who participated and found value in the series. We hope to see you again at the upcoming activities organized by the National Competence Centers. Thank you. This is Sezen from NCC Turkey, and hope to see you again. Bye.
Thank you, Sezen, and the entire TÜBİTAK team.
I cannot understand you, Dusan. Could you please repeat?
Oh, is now better?
Yes.
I just said thank you, personally, Sezen, and the entire TÜBİTAK team for your effort.
Okay. Thank you, Dusan.
Yeah.
Bye.